All right, hey everybody. We are going to do another example. This is a bit of an application problem. So this kind of problem that we'll go through in detail in a moment, right? You'll see tons of these out there, and I don't want to give the impression that this is a particularly important problem. It's an interesting problem. It's not unimportant, but it's a good chance to, it's got concepts in it that most of us are able to understand, right? A lot of times we have some physics examples and things like that. If you're not that familiar with physics, it might be difficult, or some chemistry problems or biology or something like that. But this is a nice one that I think we can all wrap our heads around, but does let us see how we can use differential equations in applied situations to understand something about the universe. Okay, so here's the problem. We've got a tank that holds 2,500 liters of pure water, and it's got 15 kilograms of salt dissolved in it. So it's a 2,500 liter tank, 15 kilograms of salt, and there's a brine pouring in. So this is just a water mixed with salt that has 0.5 kilograms of salt per liter is the mixture, the concentration of salt, poured in at 10 liters per minute. The tank is thoroughly mixed and is drained out at the same rate the brine enters. So 10 liters are pouring out from the tank. We want to find a function that models the amount of salt in the solution at time t. And then there's a question, if this process continues for a very long time, about how much salt will be in the solution. Okay, so we'll come to those in a bit. We first really need to understand the situation. So I'm going to start with a little picture. We've got ourselves a tank, right? And this tank is holding water. So we'll have 2,500 liters. And in the beginning, we're going to have 15 kilograms of salt. Okay, and then we've got some water flowing in. All right, so there's flow in, and the water flowing in has 0.05 kilograms per liter at, what did we say, 10 liters per minute, right? And then there's also an outflow of thoroughly mixed water coming out at, let's be consistent, let's use black for that, 10 liters per minute, right? So a couple of things to understand. First of all, notice 10 liters in, 10 liters out. The amount of water in this tank is going to stay constant. This phrase, thoroughly mixed. What we're to understand from that is, right, as you can imagine, the concentration of salt in the tank is changing, right? We've got some salt when we start. We're pouring salt water in, maybe at a higher, maybe at a lower concentration. We have some work to do, but it's going to change the concentration of salt unless it was the exact same concentration coming in. What we're going to assume is that it's essentially all the same concentration, right? If we were really studying this in detail, we'd have to dig into some like fluid dynamics. Where's the salt going to end up? Is the stuff flowing out going to be higher than the concentration, the average concentration of the tank, or lower, or something like that? We're just going to assume there's a concentration in the tank at each moment, and the water flowing out is at that concentration. Okay, so there's our problem. There's our setup, our little picture. Right, this is maybe some industrial setting, and for whatever reason they need water at a certain concentration, and maybe this is the easiest way to do this for some reason. All right, what we're looking for is a function that models the amount of salt in the solution at time t. So let's name the thing we're looking for, right? This is always among our first steps. So I'm going to call it S for salt, and this is going to be the amount of salt in the tank, right? In the solution in the tank at time t. And let's say that the units of S of t are going to be kilograms, and t, I'm going to go with minutes because the rate at which water is going in is in minutes, liters per minute. So probably that's going to be easiest than having to switch it to some other time increment. And then the problem didn't ask us to do anything in particular around that. Okay, how do we start coming up with this function? How much salt is in a tank at any particular moment, right? We know how much is there at the beginning. There's 15 kilograms. A minute later, we've poured in, right, 10 liters at this solution, but at the same time, we're letting some out. So it's kind of hard to understand how much salt has gone out. We don't know. The water coming out is at the current concentration of the water in the tank, but that's constantly changing, okay? So here's the tactic we're gonna take. Let's look at S prime of t, or ds dt, right? What does this represent? This is the rate of change of salt in the solution. Let's say maybe amount of salt in the solution. And it's going to have units, just looking at ds dt, right? It's how much does the kilograms of salt change per minute, right? The units of the input. So that's what this piece is going to be. Knowing the units, I think, often gives us a little bit of a hint of how we might proceed, right? And it certainly tells us if we're doing something wrong, if our units don't work out correctly. All right, let's think about this rate of change. There's two competing things changing the amount of salt that are in there, right? There's how much is coming in, the rate of salt in, minus rate out, right? Now, these two rates are changing themselves, possibly, right? We got to work through all the details. It's going to turn out one of them's changing, one of them's constant. But in general, right, let's pretend they're both constant to talk about it for a second. If I was adding 10 kilograms of salt each minute on one end, but taking out 5 kilograms of salt each minute on the other end, in total, I'd be adding 5 kilograms of salt every minute. That would be the rate of change. Of course, these might not be constant, so it's going to be a little bit more complicated. All right, let's figure these two things out. Let's talk about rate in. Well, the rate in is this top spigot. We want our rates, remember, in kilograms per minute. What I know is that I'm sending in 10 liters of water, or of brine, I should say, every minute. And that brine, each liter of it has 0.5 kilograms, right, per liter. So each one has a little bit of salt in it. Each liter has a little bit of salt in it. And we get 10 liters every minute. That means we get 10 times that little amount in each liter every minute, right? So just looking at the units, notice the liters cancel. We get 10 times 0.5, which is 0.5. And my units are kilograms per minute, okay? So there we see our rate in is constant, and that makes sense, right? We're told it's the same concentration going in with the same flow the whole time. So of course, the same amount of salt is happening each time, all right? Let's use this to understand how to figure out the rate out. Right? Well, we're gonna start with the same thing. We're sending 10 liters per minute out, right? How much salt is coming out with each of those liters? Well, it depends on the concentration, right? This number here is kilograms per liter. Well, what's the current concentration going to be? It's going to be the amount of salt in the tank divided by the amount let's say number of liters, right? That's just what a concentration is. Well, this is pretty straightforward. We've got 10 liters per minute, just carrying that part of this over. The amount of salt in the tank, we don't know. It's changing, but I gave it a name. We've been calling that S of T. So this is S of T divided by the number of liters in the tank. That's 2,500 liters. And let's give, remember, S of T is in kilograms. So our rate out looks like, doing a little math here, a little computation, 10 over 2,500 is going to give me 1 over 250 S of T, and our units will end up being kilograms per minute as we wanted, right? The liters again will cancel. We've got liters here, kilograms per minute. All right, there is our rate out. So now we have a nice expression for S prime of T. The rate in, I'm going to drop the units now. We know the units of these two things match, so we can look carefully at what we're, let's decide. I've got decimals and fractions going on. Let's fix on one of them. So I'll call 0.5 1/2. That's our rate in, half a kilogram per minute, minus 1 over 250 S of T. And lo and behold, we have a differential equation, an unknown function S and its derivative S prime, okay? So now we see where this all led to. We still have to solve this differential equation, but we now know that we're in the realm of differential equations. So let's do a little bit of work. I'm going to write this as ds dt. Let's write this as 1/2 1 minus 1 over 125 S of T. So I'm trying to make some decisions right now about what's the most convenient way to write this. I don't like what I just did. I'm taking back factoring out that 1/2. I don't know if that's smart or not. We'll see what happens. I think the most convenient way to write this whole thing would be 125 minus S over 250, right? Finding a common denominator, right? This 1/2 is 125 over 250. I feel like this might be nice. I don't know. I haven't finished working this problem out yet, so I'm going to write it this way. And I'm also going to drop the of T for now. We know that S is a function of T. I just want to make this a simpler thing to work with. So now what happens? I've got a separable equation, right? I can think of this in a multitude of ways. I think the easiest way is going to be to do the following. Take 1 over 125 minus S to the other side and leave 1 over 250. Oops, I forgot my ds. Right, so now I'm just following the little map we've made for how to solve separable equations. I've got the t part. There's no t appearing, but I can think of it as the constant function in this case, and the s function on this side. And now I'm taking an antiderivative of both sides, okay? All right, so the right-hand side is pretty straightforward. This is gonna be 1 over 250t plus a constant. Here, I'm gonna have the natural log of 125 minus the absolute value of this. But we're gonna need to pick up a negative, right? If we take the derivative of this, we get our 1 over 125 minus s, but the chain rule would give us a negative that we don't want. So there is my expression, which is strangely to the side. Let's move it over. Okay. All right, we are on our way. Now we're just going to solve this equation for s. I'm going to start by multiplying both sides by a negative. So now I'll have the natural log, absolute value of 125 minus s is equal to negative t over 250. I'm just sort of simplifying that. I'm going to play my usual game of, I could write negative c. It doesn't matter. C can be anything at this point. And so, right, if it's -2, +2, the negative in front of it doesn't matter. We can work it out to be whatever. It's an arbitrary constant, so it doesn't need to have a negative in front of it. So I'm just going to keep it like this. I use the definition of natural log. So this statement is equivalent to the statement right? So we've got this in our exponent. As we've seen, this plus c can become an arbitrary constant in front of this, right? Using the properties of exponents. And at this point, I can also drop the absolute values because that arbitrary constant can absorb the plus and minus of this, of the absolute value here, right? It'll become pretty clear what we want because this is going to be an amount of salt. We know in the end we're going to have only positive amounts of salt. We'll figure out what this constant is when we get to the end. All right, now I just have to do some algebra. If we work this out, we will get S is equal to 125 minus AE to the negative T over 250, right? Just adding S to one side, subtracting that big expression to the other side. And this is the function, or at least this is close to the function that we were solving. We now have a general solution to the differential equation that we started out solving, right? In other words, we have a family of functions because right now we don't know the value of A. So changing the value of A would change what this function looks like, okay? How do we find the value of A? Well, it wasn't explicitly stated, but there is an implied initial condition in here, right? The phrase initial condition wasn't used, but remember what S is. It's the amount of salt in the tank at time T. I guess more specifically, I should say something like T is the moment T starts running, the clock starts running when we turn on this inflow and outflow of water. So at the moment we start this process, we know exactly how much salt is in the tank, 15 kilograms of salt. So S of 0, which is 125 minus e to the 0, that becomes a 1, so just 125 minus A should be equal to 15, which means that A is equal to 110. Okay? And both of these should be in kilograms. That should work out. We can see the S here as units of kilograms, its absolute value. Well, yeah, that tracks. So now we have the particular solution. This function is S of t is equal to 125 minus 110 e to the negative t over 250, right? So this is giving us our kilograms of salt at time t, where t is minutes after we start the process of adding and subtracting water to this tank, okay? So that is the solution to the first part of this question. The second part asks, what happens to this tank as time goes on, right? What happens to, let's see how exactly how it was phrased. If the process continues for a very long time, about how much salt is in the solution. So what we're really asking here is, as we let this flow for a long, long time, what happens to S? In other words, I want to start looking at what is the limit as t goes to infinity of S of t. Well, this is the limit as t goes to infinity of 125 minus 110 e to the negative t 250. And if we remember our limit rules, we get the limit as t goes to infinity of 125 minus 110 limit as t goes to infinity, e to the negative t over 250. Well, the limit of the constant, nothing changes about the number 125 as t gets bigger, so this is 125. This piece, e to the negative t over 250, goes to 0. We're getting a 1 over t to the 250, which is getting larger and larger and larger. That fraction is getting smaller and smaller and smaller. So as time goes on, the function s of t gets closer to 125, meaning the longer we let this run, the closer the amount of salt in that tank gets to 125 kilograms. One thing to note, if we take that 125 kilograms and divide it by 2,500 liters, we get 0.05 kilograms per liter, right? So we're heading towards that concentration of salt, right? Having 125 kilograms in a 2,500 liter tank is the same as having a solution, a 2,500 liter solution at a concentration of 0.05 kilograms per liter. That number should be familiar. It's the concentration of water we're putting in, right? We just keep putting in this concentration of water, of salt water. The tank we're pouring it into starts to look more and more like that thing we're putting in. In the first minute, it doesn't, right? It starts out with a much smaller concentration, 15 per 2,500 liters, which is a smaller fraction. But as time goes on, we get closer and closer and closer to that number, to that same concentration. Okay, that's it. That's a long one. It's a classic type of differential equation. All right, that's it. Thanks, everybody. I will see you next time.